Welcome to Screeps Design Session, where we'll discuss a feature of a Screeps bot, dig into its implementation, and talk about its strengths and weaknesses. Today, we'll be looking at one way to store data that persists over multiple ticks: segmented memory. First, we'll talk about what it is and why we should even bother implementing it. The biggest reason is just to save CPU, and personally I was able to save about 15% of my total. Then, I'll explain the path I took in building out the code. Let's dive in. The most common way to store data is through the built-in memory object that Screeps provides for us. We can store JSON in this object, and it will stay there from tick to tick, but using it isn't free. At the end of each tick, Screeps will take the global memory object and transform it into a string using the json.stringify method. Additionally, this string is automatically decoded back into the global memory object using json.parse at the beginning of each tick. This results in a potentially large CPU drain, depending on how much memory your bot is actually using. We pay this cost each tick, regardless of whether memory has even changed. We can use memhack, which involves storing our memory object in global. This allows us to avoid the decoding each tick. We still have to pay the encoding cost each tick though, unless we're willing to store our data less frequently and risk losing some on a global reset. We can almost entirely eliminate the cost of storing and retrieving data by instead utilizing segmented memory. There are two main benefits to using segmented memory. The biggest one is that we only pay the price of json.parse once upon global reset. From there, we're responsible for keeping our heap-loaded data up to date, but we never need to query our segments again. A second benefit is that we pay the price of json.stringify only each time a portion of our data has actually changed. Not only that, but we only stringify the portion of data which changed rather than the sum of our entire memory. So in other words, not only are we doing a less expensive operation, but we're actually doing it less frequently as well. So what is segmented memory? It's basically just an array of 100 strings, each accessed by an integer index, like any other JavaScript array. We can think of it as 100 buckets, where each bucket always holds some string. By default, that'll just be the empty string. So how do we go about storing memory into segments? We could just take our entire memory object, turn it into one big string, and store it in buckets one by one until all our data is stored. But this approach removes most of the upsides of using memory segments. Just like with the traditional memory, we can't update just the parts of our data that have changed, and we have to read all our filled segments in order to decode it back. So how can we utilize segments to improve our performance? We can still think of our data as one big JSON object, or even as a set of JSON objects corresponding to each of the fields we put in memory. But now, we want to separate our memory into chunks that are strongly correlated, and turn each chunk into a separate string. We can still use JSON stringify for that, but now we'll be calling it on a bunch of smaller strings instead. Then, we can update only those chunks that have changed into segments. We'll see better performance gains the more closely linked to the update frequency of the data. The ideal case would be all the data in the chunk is always updated at exactly the same time as each other, but that's probably impossible to actually achieve. We should still try to group our data as best we can. Data which updates rarely should be in a separate chunk as data which updates every tick. The better the separation, the better the gains will be. For example, let's say we have a process which runs every 30 ticks. We could group all the resulting data of that process into a chunk, and we'd only have to call stringify once every 30 ticks for that chunk. Okay. So now we have various chunks of distinct and hopefully somewhat optimized data, ready to be placed into segmented memory. Let's look at the structure we're provided with in the API. This will provide our constraints, which will in turn determine how we design our implementation. Basically, we have 100 segments that can each contain some amount of text. Each segment is accessed by a numerical index, 0 through 99. And we can access up to 10 segments per tick, regardless of whether we're reading or writing. This is done by calling RawMemory.setActiveSegments and passing in an array of segment indices which should be active during the next tick. Those segments which are already active in the current tick are all accessible in the RawMemory.segments object. We can also just assign something to RawMemory.segments at a specific index, provided we haven't hit our 10 per tick limit yet, even if we didn't make it active this tick. Just make sure not to have more than 10 elements in our active memory at the end of the tick, or your code may blow up. How big is each segment? The API says each segment can hold 100 kilobytes, but that's actually not true. In reality, the Screeps source code just checks to see that the string length is less than or equal to 100 times 1024. So each segment can hold 102,400 characters. and we have 100 segments, so that's a total of 10,240,000 characters across all our segments. Given that we don't have to use JSON.stringify and could compress and decompress our text as we want, this is, quote-unquote, a stupid amount of storage space for one bot to have. Now, we have a bunch of chunks which are ready to be stored in segments, but we have a problem. Which segments do we put our data in? We need some way to keep track of what we're storing in our segments. Specifically, we need to know which segments are empty and which ones are already being used by another chunk. We could imagine having a map which associates each segment index to a state, either empty or full. Then we could just store a chunk into the first empty segment, right? Except if we've already written this data to a segment, we should be overriding that data, not using a new empty segment. So we need to know which segments each chunk is currently stored in. We need to know two things actually. First, given a segment index as a key, what chunk, if any, is being stored there? And second, given a chunk, which segment indices contain it? So we have two resulting maps, what I call buckets, which maps each segment index to the chunk label held within it, and index, which maps each chunk label to an array of segment indices that contain it. Taking a step back for a moment, these two maps are what I consider segment memory metadata. That is, it holds no actual data, but instead contains structural data which we need to operate our segmented memory implementation. We could store this in a reserved hard-coded segment if we wanted, to avoid using memory entirely, but I found that the volume of data used by my metadata was small enough to just use traditional memory. Okay, so we've set up a way of storing which segments are reserved by which chunks, and vice versa. Now, how do we actually save and retrieve the data? So far, we basically just have a class that holds those two maps. Let's say our code has determined that some data should be saved and turned into a string. This would be the equivalent of setting a JSON as a member of memory in our old implementation. It will tell our class, here's some text for the chunk room info, let's say, stored in memory. The function enqueueWrite should be responsible for deciding which segments to use and splitting our big string into sections for each segment. Finally, it should write the actual data to the segment. We can do all that, but there's an issue with the last step. What if writing to those segments would put us above the maximum we can write to each tick? We never want to write to only part of a chunk, since that could lead to unparsable strings when we try to read back from it. Instead, we can create a write request, which stores data mapping each segment to the portion of the chunk that should go in that segment. We can then add the write request to a queue of requests, which could be processed as soon as possible. Then each tick we can process those requests and do the actual writing to segments. More on that later. And you can see we've also delegated the allocation of new buckets to a separate method. It's relatively simple. It just iterates over our buckets and finds the first empty ones, adding them to a list until we've found enough. So now let's worry about actually processing the write requests. We'll want to do this as part of our main loop each tick. Could we just iterate over each of our requests and store them in segments? Not quite, because once again we're limited to writing to 10 segments each tick. We'll have to keep track of how many unique segments we've written to each tick as we iterate. As long as the number of segments written to, including the current one, isn't greater than 10, we can do the actual writing. This is pretty simple because we already split up our text when we made the write request. We can just iterate over each piece and assign it to the already allocated segment. As I mentioned earlier, assigning it to the segment will work, even if we didn't call setActiveSegments with that segment ID in the previous tick. It'll be saved correctly, and it will make that segment active going forward. Also, we'll need to do a bit of cleanup to ensure that if we're using less segments than we were before for a chunk, we should delete the stale associations and mark the old segments as empty so that they can be reallocated in the future. We want to make sure that our two maps are accurate and up to date after each write. Lastly, we call rawmemory.setActiveSegments with an empty array passed in to ensure that the next tick will have 10 new slots available to write to. Otherwise, the ones we've written to this tick will remain active and count towards the next tick's limit. So our data should be storing correctly. How are we going to read the data in when a reset occurs? Essentially, each tick will have some segments that were set to be active from a previous tick. So we'll check all those active segments and see if any of them need to be loaded. But we might be loading a chunk over multiple ticks. We'll need some temporary storage to hold the strings before we can combine them and put them where they belong in our code. Anywhere on the heap should be fine for that. We can do a check to see if after loading all the tick's active segments, maybe some chunks have fully loaded. If so, then we should combine those strings and call our callback and do read for ID. This is where we'll decode the string back into JSON and do whatever our code needs to do with the data. And finally, we find which segments we haven't read yet but have active data according to our buckets map. Then we'll load as many of those as possible for the next tick. So now let's look at that doReadForID method. We'll leverage the fact that each chunk has a unique label and use it to figure out which portion of the system to load the data into. Now, at this point, we have a potential issue. In any given tick, we might have only loaded some chunks, ran out of active segments to read, and left other chunks unloaded. My strategy is just to wait until all chunks have loaded in order to actually run my bot. Your code might be capable of operating with only part of memory loaded, but that was too complicated for my codebase, so we'll leave it as a tech debt for the next engineer. If you're migrating from traditional memory, it might be a good idea to perform the migration in the following steps. First, save into memory like before, but also call and queue write with your new chunk of data. Essentially, save into both. Verify that the data saved into segments is correct. Then, deploy code which saves into both, but loads from segments. At this point, perform testing to ensure that the data is still correct. I'd recommend doing several rounds of generating new data, ensuring it saves correctly, and then triggering a reset and verifying that the new saved data is also loaded back correctly. Finally, once everything seems to be working, deploy your code which both writes to and reads only from segments. Now you can delete your old memory, and once you do, you should be seeing huge CPU savings. Now I've just got some final notes. If you look through the code, you'll see something called global.heapStorage. This is just volatile memory, and it could live in segment data along with our loaded data map. I only have it in that global object, just because that's where most of my non-stored data lives. We use a queue to ensure that the data is saved somewhat sequentially. This is a common data structure, and its functions are easily found by Googling. I considered it out of scope for this video. You could use a list if you want, it just might be less performant. You might also have noticed that the index and bucket maps are actually records, rather than true JavaScript maps. That's because in TypeScript, records are just JavaScript objects, meaning they'll be successfully turned into JSON with the default stringify. Maps and my queue won't be, so we can just store our class instance somewhere in memory and it will be stringified without that data. So when you see me using a map or a queue, it's because I don't want it in memory. I also have a constraint, which ensures that each chunk is no more than 10 segments large, so that each write operation can be done in a single tick. That's to ensure that no partial data is ever written. This can be avoided by using memory to temporarily store our write requests, rather than have them live in global. This would also ensure that a global reset wouldn't delete any temporarily queued writes. However, I'll leave that as an exercise to the reader. Another thing that we'll want to keep in mind is that if we call and queue write every tick, we'll be stringifying our data anyway, where most of the costs will be incurred. Instead, we should probably keep track of whether the data in each chunk has been updated with a flag, then we should only call and queue write when needed. As we chunk our data into smaller and smaller pieces, the performance benefits should go up, as we're stringifying less and less data, which hasn't actually changed. But we'll be occupying more segments and potentially lowering our overall storage capacity. It just depends on whether you need to minimize your CPU at the cost of overall storage space. Well, that's all I've got for you today. I hope this helped you implement your own heap storage, or helped you integrate my framework into your codebase. Lastly, if you have any feedback for me, I'd love to hear it. You can drop those in the comments and I'll be reading those, what worked, what didn't, and what you'd like for me to cover next.